We're going to look at another portion of this exercise of looking at Descartes' rule of signs. Quite honestly, I don't know how to really pronounce the word. It looks like to me Descartes, and I've called it that for about 50,000 years, so I'm going to continue to call that that. That's how you really say that. I think it's a French guy. How to say his name, I'm really not sure. But if we look at a question in our textbook described as 65, in this case, it's simply describing the sign changes in the polynomial from left to right. So if I move from left to right, this is a positive sign, this is a negative sign, this is a positive sign, this is a negative sign, this is a positive sign. So we see four changes of signs moving from left to right. So we talk about the number of possible positive zeros, which we've talked about in class many times. But if we got four possible changes of sign, we can have up to 4 zeros or 2 zeros or no zeros that are positive. So this is number of possible positive zeros. I forgot to mention that, and that's based upon the sign changes from left to right. So we can see there's going to be a possibility of 4 possible positive zeros or 2 possible positive zeros or 0 possible positive zeros. So when you do that, I'm talking about possible positive zeros that are positive, meaning like a positive number. Like if we have 4 zeros of 4, 3, 2, and 1, those are all positive zeros. So the number of possible positive zeros are going to be 4 in this case, or 2, or 0. They go down in groups of 2. Now, we've talked about this in class a few times. Like if we have imaginary zeros always come in pairs, and that's why I'm going to drop down from 4 to 2 to 0. I'm probably going to give you another question that's very, very specific in terms of the imaginary zeros of a polynomial. But for right now, just in this next exercise of looking at Descartes' rule, let's look at utilizing the rule by looking at the question. Now, how to determine the number of possible negative zeros? Well, I know the answer is going to be none, because if there are 4 possible positive ones, and there's 4 of them, the maximum number of zeros that a fourth degree polynomial can have is 4. So if they are positive, there will be no negatives. But let's go through the process of just demonstrating that and seeing that there are no negative zeros of the polynomial. And we do that by evaluating this at a negative x. So let me back up again at this. There's 4 or 2 or 0. Imaginary zeros always come in pairs. So if of these 4 zeros, and 2 of them happen to be imaginary, then I can't have 4, I'll have only 2. Then if those 2 are imaginary, then I can only have 0. So they always drop down in groups of pairs, always from decreasing by 2 each time, 4 to 2 to 0. So if it was happen to be 3, it'd be 3 or 1, and those would be the only choices. But we'll do that in a second. So evaluating this at a negative x, I would do 2 a negative x to the 4th power minus negative x to the 3rd power plus 6 negative x to the 2nd power minus x plus 5. So we're evaluating this at a negative x. Being careful as to how we do this, a negative x to the 4th is 2x to the 4th. A negative x to the 3rd is a negative x to the 3rd. Negated becomes a positive x to the 3rd. And this would be a 6x squared. Negative x squared would be positive. A negative of a negative would give me a positive x and then a positive 5. So looking at the sign changes, now this is due to the possible negative zeros, and again it's the same sign changes. 1, 2, there are no sign changes, they're all positive, so they're all positive across the line, so there are no negative zeros, meaning negative, like negative numbers, like numbers less than 0. Those are negative zeros. So this is 65, and that's all there was to it. So there are no real negative zeros, but there could be 4 positive real zeros, or 2 real zeros, or no real zeros. And quite honestly, many years ago, when this is really apparent, this is very helpful for the student of years ago before calculators. So now we have calculators, these Descartes Rule, things like this are not really majorly apparent, that are very important, but we still teach it because I think it's a good piece of information to know, because I'm not a great calculator guy, as you might know by now. I'm just not a real fan of it, especially in terms of learning and understanding recalculus material. Now, looking at 66, I'm going to take the equation face up, just as it is, and check the sign changes. There are no sign changes from here to here because they're both positive. Then we go to negative. That would be a 1 sign change. Then a positive would be 2 sign changes. Then a negative would be 3 sign changes. So there could be 3 possible positive zeros, or there could be, if 2 of those 3 happen to be imaginary, then there could be 1 possible positive zero. So these are the choices. There could be 3 of them, or there could be 1 of them. Then, since I know it's a 4th degree polynomial, just logically speaking, when I check for the negative zeros, I'm going to evaluate this at a negative x, and I'm going to probably predict that there's going to be 1 possible negative 0. So, evaluating negative x, 3 at a negative x to the 4th power, plus 5 negative x to the 3rd power, minus 6 negative x to the 2nd power, plus 8 negative x minus 3. We're working our way across. A negative x to the 4th power will be 3x to the 4th. This will be a negative 5x to the 3rd, and negative x 3 times will be a negative times negative would be a negative x to the 3rd multiplied by 5. Then this would be a negative 6x squared minus 8x minus 3. So looking at sign changes, the only sign change we have is going to be 1 sign change, and the rest of them are going to be negative. So this would be 1 possible negative 0 based on the sign changes after you evaluate at a negative x. Maybe look at another one of these. Looking at the sign changes from left to right, this would be 1 and this would be 2. So there will be 2 sign changes. So the number of possible positive zeros would be 2 possible positive 0. Or going down in groups of 2, or there could be no possible positive zeros. So going down in groups of 2, from 2 to minus 2 takes you to 0, so it's 2 or 0, meaning the 2 that possibly could be positive zeros, if they happen to be imaginary, then there won't be any real zeros. There would just be none. Now looking at this as a 3rd degree polynomial, the maximum number of zeros a 3rd degree could have is 1. So when I evaluate this at g at a negative x, checking for sign changes for negative zeros, I'm going to predict this is going to leave me with 1, because if this is 2 of them, they had to be positive, there could only be 1 more negative 1 at most. So that's my prediction. Let's do the evaluation. negative x to the third power minus 5 negative x plus 8. Negative x 3 times would be a negative 4x to the third plus 5x plus 8. And you can see again, there is only one sign change as we proceed from left to right. So it could be one possible negative 0 at most. And there can't be, going down in groups of 2, that would take me to a negative 1. Obviously, I can't have less than 0 negative zeros. So it's either 1, and it's not going to be 0, and it'd be 1, and that's it. Maybe looking at 68 as well. We got g of x is equal to 2x to the third minus 4x squared minus 5. So if I look at this in terms of sign changes for the number of possible positive zeros, positive to a negative is 1, and negative to a negative is no sign change. So there can only be one possible positive 0. Now my prediction for the fact that this is a third degree polynomial, at most it can have is 3. So if there's only one possible positive 0, that means there could be 2 possible negative zeros. So let's see if this confirms. G at a negative x would be equal to 2 at a negative x to the third power minus 4 negative x to the second power minus 5. This will leave me with a negative 2x to the third, a negative 4x squared, minus 5. So looking at the sign changes, I work my way across for the negative zeros. My prediction is saying 2 more negative zeros did not turn out to be the case. There are no sign changes in the evaluating this at a negative x, so there are only one possible positive 0, and there are no negative zeros. So we have no negative zeros, but we have one possible positive 0. Because we did the evaluation at a negative x, there are no sign changes, there are no negative zeros. I'm going to stop this for Descartes Rule, or however you pronounce the name.